This collapsing network reflects a change in how we build with AI. Engineers are moving away from isolated text generation models towards fully integrated agentic systems. An agentic system is a programmatic environment where the outputs of a large language model directly dictate and control the execution workflow. The model generates text, and that text executes code. But handing over the workflow introduces severe architectural risks. First is the loss of predictable state management. When an LLM executes multiple loops, tracking the precise state of the application becomes incredibly difficult. The second risk is the threat of infinite cost loops. Unconstrained reasoning cycles can trigger rapid, continuous API calls, draining budgets in minutes. Third, autonomy creates critical security vulnerabilities. When models execute external tools without rigorous oversight, they can expose sensitive data or trigger unauthorized actions. The engineering solution is to build rigorous architectural scaffolding. We have to constrain the LLM's non-deterministic nature within strict deterministic boundaries. We are going to build this scaffolding from the ground up. First, predefined code workflows. Next, standardized tool protocols. Finally, a 12-plane trust system. This requires a transition from the single prompt to the architectural scaffolding that defines how these models interact with code. This control flow schematic illustrates a workflow, the most restricted form of agentic design. Notice how the yellow LLM nodes are strictly orchestrated through these predefined blue code pathways. In a prompt chaining workflow, complex tasks are decomposed into linear subtasks. Data moves from one LLM through a deterministic gate directly into the next. You would deploy this for a multi-step content pipeline. One model generates an outline. The code gate checks it against brand guidelines, and the next model drafts the final text. Next is the routing workflow. Here, an input is triaged to a specialized model based on classification. If a user submits a query, the router analyzes it and sends it down one specific path, activating either billing, technical support, or the sales LLM. In parallelization, a single input is sent to multiple specialists concurrently. A deterministic code aggregator then collects these concurrent outputs. It evaluates the different responses and synthesizes them into a single unified result. Finally, we have the evaluator optimizer workflow. This creates a direct feedback cycle between a generator model and an evaluator model. This mathematical loop reduces the probability of compounding hallucinations. By forcing the generator to refine its output against the evaluator's criteria, error rates drop significantly. These four workflows maximize execution reliability. However, their rigid code paths lack the autonomy required to adapt to dynamic, unpredictable environments. This diagram shows the exact threshold where a workflow becomes an agent. We remove the fixed code path, allowing the LLM to dynamically direct its own processes. Without predefined pathways, the agent evaluates its goal and dynamically selects its own tools. It interacts with the environment and receives real-world feedback. This data triggers a new, unprompted cycle of reasoning and tool selection until the task is complete. But this flexibility creates an integration bottleneck. Engineers are forced to write custom glue code for every possible external API the agent might need to access. Managing autonomous systems at scale requires replacing custom tool integrations with a universal communication protocol. The solution is the Model Context Protocol, or MCP. It functions as the USB-C of AI tooling, designed to solve this exact integration problem. This architectural diagram begins with the MCP host application. The host is the foundational software, or agentic framework, managing the entire runtime. Inside that host boundary sits the MCP client. From this client, a thick, standardized pipeline forms a universal connection outward, seeking external resources. That pipeline locks into the MCP server, an isolated provider supplying specific tools and context. These servers can be deployed in two ways. They can run locally on your own machine to access the file system, or they can run remotely to query services like the Google Maps API. By decoupling the tool logic from the agent implementation via MCP, engineers can standardize how LLMs access diverse external capabilities without rewriting integration code. This diagram illustrates the necessary boundaries for deployment. Giving an LLM autonomy and standard tools is a massive liability without a comprehensive governance architecture to contain it. The first layer is the user intent plane, filtering incoming data. The data then drops to the reasoning plane. Here, a linear prompt is converted into a structured, verifiable branching task graph. Next, the memory plane manages state machine hydration, feeding state data back into the core loop. Before any tool actually executes, the MCP tool plane steps in. It acts as a strict firewall, enforcing schema validation and strict permissions on all outbound requests. The guardrails plane enforces hard constraints and confidence thresholds. It actively catches hallucinated logic and blocks out-of-bounds actions. All of this surrounds the execution runtime at the core. It strictly manages the state machine flow, cycling sequentially from planned to executing to verifying. An autonomous agent is only as safe and reliable as the 12 planes of infrastructure that contain it. To see this in practice, we can map these frameworks onto a multi-agent proof of concept, a system autonomously designing, coding, and testing a financial application. This side-by-side comparison shows how the theoretical architecture maps to actual code. The system's YAML configuration files directly function as the system's reasoning plane, setting the operational logic. Specialist agents operate within the coordination plane, executing verified handoffs between design lead and back-end engineer nodes. Generated code routes to an isolated Docker sandbox, satisfying the execution and guardrails planes. Finally, the governance plane logs every decision for root cause analysis. The focus has moved beyond prompt optimization. Engineering success now depends on the holistic design of the workflows, MCP connections, and trust planes. Mastering these architectural constraints is the only way to transform non-deterministic LLMs into deterministic, commercially viable software systems.